All right, so we started here talking a little bit more specifically about perfect competition. We've discussed it at length in class, but I feel like you might do well with some additional material, and especially in the context of actually calculating profits, because this is what I ask you to do on the next assignment, and it'll be something that you definitely want to understand how to do for the third exam. And so here we have a very traditional short run cost curves for a perfectly competitive firm. The one sort of point of difference here is that you see an average fixed cost curve, which you don't normally see in these sort of contexts, but they put it here, and so you can again see that its behavior is exactly what we would expect. But the sort of three main curves that we're mostly interested in is this average total cost curve, this average variable cost curve, average variable cost curve, and then this marginal cost curve. Again, just sort of remind yourself what these curves are, and sort of what they represent. And so, if we're looking at the cost curves, they should make some intuitive sense. As we increase more, we see both average total cost and average variable cost fall and then rise. And again, we see average fixed cost fall. And then if we just sort of look at the behavior of marginal cost, one of the things that we'll notice, and this was pointed out previously, but it's sort of worth repeating, that the marginal cost curve intersects the average variable cost and average total cost curves at their minimums. This is an important mathematical sort of point, but it's also an important economic point. It's important from a mathematical perspective because it makes complete sense. It's logical. If we think about marginal cost as something like, say, the score you make on your next exam, and then we think about average total cost as being your averages on all exams up to this point, we know, from the law of averages that if I do better on the next exam, then my average will rise. And so when marginal cost is above average total cost is rising. So if I do better on the next exam, my average will rise. If, on the other hand, I do worse on the exam and my marginal cost is below, I notice that my average is being pulled down. And so this is important not only from that kind of mathematical perspective, but also important from an economic perspective, because this intersection between marginal cost and average total cost creates what we call the break-even point. It's the point at which a firm would earn exactly zero profits. And as we've talked about in class, this break-even point has many implications, sort of when we think about competitive markets as they move from the short run into the long run. But let's sort of move on. Again, we just want to sort of refresh ourselves with the competitive market assumptions. The sort of big takeaway from our assumptions is that competitive markets, the firms within them are price takers. In other words, they take the price from the market. All right, so we can take through sort of a numerical example that just sort of comes from a spreadsheet type situation. And so, you can sort of get an idea for what's going on here. So the firm's producing more. As the firm produces more and sells more, as expected, their total revenue rises. But then, of course, their total costs are rising as well. And so this is really that balance that firms have to strike. They have to sort of assess kind of to what extent attempting to sell more relative to how much it costs them to produce, and whether that makes sense to actually produce and try to sell more relative to their costs. So what we really want to focus here is on this idea of marginal revenue equaling marginal cost. And so here, with the green column here, we can see that marginal revenue is constant. That is, it doesn't change because marginal revenue is simply the price that the firm charges for their product, right? That's the change in total revenue divided by change in Q. It's just the price that the firm charges for their product. And then when we look at marginal cost, we see that marginal cost sort of starts out a little high, falls, and then gets very large towards the end. And of course, what we're looking for is that profit maximizing point where marginal revenue equals marginal cost. And we find that at 8 units. We can see that at 8 units, marginal revenue equals marginal cost. We can also see that at 8 units, we have a maximization of profits. And so, again, we see that when marginal revenue equals marginal cost, that this leads to a maximization of profits. Notice here that we earn the same profits we do at 8 as well as at 7. So sometimes students have questions about why we would choose sort of 8 over 7. In a sense, it sort of doesn't matter too much. Just sort of notice that marginal revenue equaling marginal cost yields the sort of profit maximizing position. And again, they're equivalent. It's not, sort of that big of a deal whether they produce 7 or 8, because at the end of the day, it's the exact same profits. So if we just follow the marginal revenue equaling marginal cost rule, that'll lead us, in a sense, to the promised land of profit maximization. Now, again, firms maximize profits by choosing a quantity such that marginal revenue equals marginal cost. What happens if they have marginal revenue greater than marginal cost? What happens if they have marginal revenue less than marginal cost? So we go back, we can see that when marginal revenue is greater than marginal cost, the firm wants to produce more. And when marginal revenue is less than marginal cost, the firm wants to produce less. And this should make sense. Marginal revenue is what the firm has coming in from the additional sell of a unit of a good, and marginal cost is what it costs to produce an additional unit of the good. And so if you're going to make money on selling your good, you should produce more. And if you're going to lose money by selling your good, then you should produce less. All right, so we can go through a quick numerical example, again, just to sort of make sure that you understand how to calculate profits. So we need 3 things. We need to calculate profits. We need a marginal cost curve, we need an average total cost curve, and we need a marginal revenue curve. And so in this particular example, again, we're going to assume that market price is $10, and so that's where the marginal revenue curve is. Marginal revenue equaling marginal cost is going to establish our profit maximizing quantity of 8 units. Again, very simple. Don't make this any more complicated than it needs to be. Marginal revenue equaling marginal cost is where we want to be. Now, in order to calculate profits, we need to find out where average total cost is at a quantity of 8 units, so at our profit maximizing quantity. And so this, of course, will be given to you as a number, so you'll just sort of need to know where to look. But in this particular example, we see that at 8 units, average total cost is $8.75. And so we have actually a little bit of a shortcut here. At the end of the day, we can basically see that profits are equal to the marginal revenue minus the average total cost times the quantity of the product. Or we can do that the longer way, and we can take 10 times 8 and then subtract off 875 times 8. Or we can notice that 10 minus 875 times 8 gives us the same answer. So it gives us a little bit of a shortcut there. And then graphically, we can visualize what profit is, and it's just this rectangle. If you think about this, total revenue is going to be 10 times 8, which would mean that total revenue is this entire square rectangle here, quadrilateral, however you want to think about it here. And then total cost is going to be average total cost times Q, and so that's that smaller square rectangle here. And then so the sliver that's left over, this is the actual profits. So if we actually calculate this, again, sort of 10 minus 875 times 8, this tells us what the firm's profits are. And when we do that, we see that the profits of the firm are equal to $10. So in this particular example, using these particular numbers, we would find that the firm is earning $10 in profit. And so this is really, that's the trick. There's nothing sort of more to it than this. If we have a perfectly competitive firm, we simply look where marginal revenue equals marginal cost. That spits out a profit maximizing quantity. We take that profit maximizing quantity, we go back up to the average total cost curve, and that gives us the sort of profit maximizing average total cost. So profit maximizing price minus profit maximizing average total cost times profit maximizing quantity gives us profit maximization. And in this particular example, profit maximization occurs at $10. Okay, next we want to talk about calculating profits under the monopolist, but I wanted to do something that I don't normally do, but I just wanted to kind of take you through and show you exactly why the marginal revenue curve looks the way it does under the monopolist. I'd mentioned in class that there's a mathematical reason to it, but I can actually show you here graphically relatively easily why. So again, here we're talking about the monopolist. If we just real quick think back to perfect competition, so the idea behind perfect competition is that firms set marginal revenue equal to marginal cost, just like we did previously, and they earn profits of some amount. Could be positive, could be negative, could be equal to zero. And the idea is that in the short run, firms respond to prices by choosing particular quantities and then earning those particular profits. If there's profits in a market, we expect firm entry, which pushes the price down, which lowers the profits of existing firms in the market. If we have firm exit, we expect profits to rise and increasing production amongst the firms existing in the market. And again, we have that long run effect of firms earning zero profits in the long run, essentially because under perfect competition, we assume only the most efficient firms make it into the long run. And you should think about this in the context of the fact that costs are the sort of linchpin of that particular decision. They're sort of the deciding factor into what actually determines how much a firm earns profits. And so as we go into the long run, only the least cost firms stick around, and we have this nice efficient outcome where all the firms earn zero profits, which of course no firm actually wants to do. Every firm probably wants to be a monopolist because then they can earn long run profits greater than zero. So again, I just want to kind of dive into monopoly here, and again, to kind of show you why the marginal revenue curve looks the way it does for the monopolist. Again, if you'll recall, under perfect competition, the marginal revenue curve is flat. We just saw that in the previous example, whereas under the monopolist, we see the marginal revenue curve is downward sloping. This is actually fairly important, and we'll get to why that is here in just a moment. But first, let's think about this. So again, we want to think about the idea that we can calculate total revenue because we're dealing with a monopolist, so that they're the only firm in the market. So we can actually calculate total revenue at particular levels of quantity on the demand curve. So we actually know what the firm can earn from the sale of their product, what their total revenue would be under various price and quantity decisions. For example, if the price were $70, then this would imply that consumers would be willing to buy 3,000 units at a price of $70. And so $70 times 3,000 units gives us total revenue of $210,000. We can compare this to a price of $60, for example, which when we do this, we see that at a price of $60, the firm now sells 4,000 units. We multiply $60 times 4,000 units, and we get total revenue of $240,000. So a $30,000 increase in total revenue when the firm produces at 60 units as opposed to 70. This is an important point because oftentimes in a monopolist, there's this sort of assumption that the monopolist just wants to charge the highest price possible. But because demand curves are downward sloping, there can actually be real revenue gains by actually dropping the price. Now, if you'll recall back to what we discussed previously, that really the determinant of whether the firm increases or decreases their total revenue depends upon where we are on the demand curve. And so when you have high prices, it oftentimes pays off, as it does in this scenario, to lower your price, whereas if you have lower prices, it can in fact pay off to increase your price. And again, we can look at this through the context of marginal revenue. So if we were to increase our price from $60 to $70, we would in fact see that total revenue would fall by 30,000 units. So there's a pretty clear incentive here for the monopolist to prefer a price of 60 units, or excuse me, to prefer a price of $60 as opposed to a price of $70. Now, we can untangle this effect by actually looking at the way in which we arrive at a $30,000 increase in revenue as we go from a price of 70 to a price of 60. So in fact, there's a $30,000 revenue loss as we go from 70 to 60 if we were to produce the same amount of the product. But of course, by dropping our price from $70 to $60, we in fact see a sizable increase in revenue coming from what we would call the output effect. So we increase output from 3,000 to 4,000. And that revenue change is 60,000. So what we see is that the total change in revenue, as we previously had stated, is $30,000. Revenue goes from $210,000 to $240,000 as the price falls from 70 to 60 units. And so the full effect there is a change in total revenue of 30,000, which would mean that the marginal revenue as we go from 70 to 60 in terms of price would be $30,000, as you would expect. And so that's how we arrived. I just kind of want to take you through and disentangle that for you a little bit. Okay, so how much does the monopolist choose to produce? As we've talked about, the monopolist chooses where marginal revenue equals marginal cost. This gives them a profit maximizing quantity, which we see here is 1,000 units. Now, what we're looking for here is we need a way to sort of calculate profits. So one of the things that we're missing is an average total cost curve. So first and foremost, we established that at a quantity of 1,000 units, that the price that the firm will want to charge is $50. Again, remember that we go from the quantity up to the demand curve to find the price that the monopolist charges. Again, the monopolist will charge the maximum willingness to pay at 1,000 units, which we can see here is $50. Now, as I mentioned, what we need is an average total cost curve in order to compute profits. And so when we add a average total cost curve here, we can see that the quantity of 1,000 units hits the average total cost curve at $35. And so if we just take a step back here, we saw that at 1,000 that the firm would charge 50 units. So again, we do the exact same thing that we did under the perfect competitor. We take the price that they charge here, which is $50. We then subtract it from what average total cost is at that particular quantity here, which is $35, the difference being $15. And then we multiply that by the profit maximizing quantity. So the profits here for the monopolist, which we can show in this shaded region, would in fact be equal to $15,000. Again, that would be 50 times 1,000 minus 35 times 1,000, which is 15 times 1,000, which is $15,000. So again, this particular this particular profit outcome for the monopolist would be $15,000, which again we can see with that sliver of a box there. Now, what can happen to the monopolist, for example, is if for whatever reason their average total costs really rise on them very quickly. And so here, even though we don't necessarily expect it, the monopolists could find themselves in a loss situation, similar to what we saw in a perfect competition when prices fell. And so here you can see that it is possible for the monopolist to earn negative profits, but there has to sort of be something that happens to their costs. Maybe sort of a massive distributor problem that causes their costs to rise very quickly. But again, we would sort of expect the monopolist to over time be able to earn long-run profits greater than zero. And again, the way we do this, we set MR equal to MC. This establishes a profit maximizing quantity. We then, assuming there's an average total cost curve, which that will be given to you, we just need to find what the average total cost is at that quantity, do price minus average total cost, and multiply that by the profit maximizing quantity. And that gives us our profits for the monopolist. Okay, and then here we're going to real quickly kind of put two situations sort of beside each other. So on the left we have the competitive industry, and on the right we have the monopoly. And we can sort of see the difference in outcomes here. So in the competitive industry, we can see that we have the normal supply equals demand outcome, which sets a competitive market price, which we call PC, and a competitive market quantity, which we call QC. Now, if instead this firm were a monopolist, and we consider the monopolist outcome, what we would see, again, we can show PC and QC there at the intersection of marginal cost and the demand curve, and then we can compare it to the outcome under the monopolist, which again is found at the intersection of MR equals MC. This causes an increase in price and a reduction in quantity, and so now we can compare the outcome of the monopolist to that of the perfect competitor. And then, of course, we also can show that under the monopolist, we have dead weight loss. So again, here's our PC and our QC. That's the perfectly competitive outcome. Then we have the monopolist outcome, PM and QM, and then we can show deadweight loss as being that triangle there. Again, deadweight loss here is the discrepancy between the profit maximizing quantity of the monopolist and the quantity outcome of the perfectly competitive market, and the height of the deadweight loss triangle is going to be the height is found here, which is where the profit maximizing price for the monopolist greater than the marginal cost of the monopolist. That's the height of your deadweight loss triangle. We also talked about this idea of consumer surplus being shifted. Previous to the monopolist, this triangle here was consumer surplus, and this was producer surplus. Under the monopolist, this small triangle here is now your consumer surplus. So consumers lose this rectangle and this triangle. This triangle, of course, goes to deadweight loss, but then this rectangle here it goes to producer surplus. So this used to be consumer surplus. Now it goes to producer surplus. Economists, again, refer to this idea as rent extraction. So the monopolist not only charges consumers higher prices and produces less quantity, but in essence does so by removing consumer surplus. So again, economists call this rent extraction. Okay, the next thing I want to talk about is just sort of take you through some additional kind of game theory that we started in class, and just kind of make sure that you're sort of understanding what's going on there. So one of the things we talked about in class was this idea of the prisoner's dilemma, and again, this is the example given in class. And so the idea here is that you have two individuals, Omar and Steve, and they have two decisions. They can either defect, which is they can admit to the crime to the police, or they can cooperate with each other and deny the crime. And then, of course, there are also the options for one of them to defect, that is, rat on the other person while the other cooperates. And again, we can see the various outcomes. So if they both rat on each other, then they both go to prison for 8 years. If they both are honest, if they both don't rat on each other, they go to jail for only 6 months. And then, of course, we can see the other outcomes of that. So again, we can think about defect here as admitting to the crime, and cooperate here as not admitting to the crime. And what we're interested in here is a couple things. First off, what do we think is going to happen in this game? And then the other thing is for us to ask ourselves, is there a potential collusive outcome? In other words, once we establish what we think is going to happen in the game, what do we think is actually possible in terms of maybe some agreement? Again, which here we can sort of see as cooperate. We can actually think about this in the context of the prisoner's dilemma being a particular type of game, not just a game about robbers and how cops split them up and talk to them about whether, sort of induce guilty pleas from the prisoners, which is, of course, what the whole idea of the game is. We actually can think about prisoner's dilemma as being a type of game, simultaneous, non-cooperative, so that the decisions are made simultaneously, meaning that I don't know what the other player chooses before I make my decision. So it's like rock, paper, scissors. That game happens simultaneously. The decisions are made simultaneously. Under the prisoner's dilemma, we assume it's non-cooperative, meaning that the two individuals can't communicate with each other while they're making their decisions. Certainly they could communicate prior to the crime or prior to whatever the sort of decision space is being made under. But then once their decisions are made, they're not talking to each other at that point. So non-cooperative. And so, again, you can see here, I mentioned that we say that in the prisoner's dilemma, the collusive outcome is preferred to the Nash equilibrium. And we talked about how to find the Nash equilibrium in class, but I want to go through this again. And the game that I want to use is the grade game. And so what we're going to do here is I'm going to take you through the grade game. We're going to talk about the various strategies. We're going to define what the Nash equilibrium is. And then we're going to talk about this idea of a collusive outcome. Okay, so the way that you want to deal with game theory is you want to develop strategies. You want to find the strategies for both players. Now here, when we have games like the grade game and also the prisoner's dilemma, we call these games what we call symmetric. That is, that both players face the exact same payoffs. When that is true, well, we only have to develop the strategy of one player because the other player will have the exact same strategy. And so under the grade game, we can just pay attention to, say, one side or the other. So we want to develop, let's say, the strategy for ourselves. And again, remember the idea behind the grade game is that I'm going to be randomly paired with someone else, and then our joint decisions are what determine our actual grades. And so in this scenario, what I ask myself is that if I think my random pair is going to pick alpha, what do I want to pick? And if I think my random pair is going to pick beta, what do I want to pick? Okay, so again, payoffs are symmetric here, so it's not super important to point this out, but typically when you see payoffs simply split by a comma, the payoff to the left goes to the left player, and the payoff to the right goes to the top player. And that's exactly what's going on here. So for example, if I were to pick beta while my pair picked alpha, I would get a C+, and they would get an A. On the other hand, if, for example, they picked beta and I picked alpha, then I would get an A, and they would get a C+. So that's how you read that. Okay, so for me, I ask myself, if my pair picks alpha, what do I want to pick? If my pair picks alpha, that means that my decision space is only these two boxes here, these two quadrants rather. And so I pick alpha and get a B+, or I pick beta, I pick alpha and get a B-, or I pick beta and get a C+. So if I think my pair is going to pick alpha, I have a clear advantage by picking alpha as well and getting the B-, because a B- is better than a C+. On the other hand, if I think my pair is going to pick beta, that puts me in one of these two quadrants. I pick alpha and get an A, I get beta, I get pick beta, and I get a B+. Again, I see that it's in fact better for me to pick alpha. This actually means that regardless of what my pair picks, it's better for me to pick alpha. If they pick alpha, I do better by picking alpha. If they pick beta, I do better again by picking alpha. So what's interesting here is that we would actually say that I have a dominant strategy to pick alpha, because in neither scenario, whether my pair picks alpha or whether my pair picks beta, is it better for me, in fact, to pick beta. In fact, it's better for me to pick alpha. We refer to this as a dominant strategy, meaning that the choice of picking alpha dominates the choice of picking beta in all outcomes of the game. Excuse me, not outcomes of the game, rather, but all decision points in the game. So whether my pair picks alpha or whether my pair picks beta, it's better for me to pick alpha. Now, let's stop here for a moment and notice, though, that there is an outcome of the game that is better than what we would call the Nash equilibrium. We call this the Nash equilibrium because both players have a dominant strategy to pick alpha. And since both players have a dominant strategy to pick alpha, this means that neither player wants to deviate from this particular strategy because they assume that each other are going to pick alpha. And in fact, when we play this game in class, out of the 80 students in class, more than 85% of you picked alpha. In fact, sort of showing how this indeed is the Nash equilibrium. Now, some people did pick beta, and again, there's no right or wrong answer here, but in terms of what the Nash equilibrium is, what we expect the game to turn out is for people to pick alpha and walk away with B-. But we notice that, in fact, there is a outcome of the game that's better than B-, B-, and that's here, this beta. So, in a sense, it would make more rational sense for both players to pick beta and go away with the B+, considering that if they're going to pick alpha, the Nash equilibrium, then they're going to walk away with B-. Notice this is exactly like the prisoner's dilemma, where if they cooperate with each other and they deny the crime, they only go to jail for 6 months. But the Nash equilibrium of this game is that we actually expect them to admit to the crime. And for the exact same reasons as we saw before. If I'm player B and I expect player A to admit to the crime, that is to defect on our agreement not to admit to the crime, then I can see that if I defect, I get 8 years, or if I cooperate, I get 20 years. So if I lied to the cops and I deny the crime, I go to jail for 20 years. If I'm honest with the cops, I only go to jail for 8 years. So I want to be honest and defect on my agreement with my fellow robber. If I think my fellow robber is going to go along with my agreement, again, I can see that, in fact, I have an incentive to tell the truth to the cops, to defect on my agreement with my fellow robber, because I would rather go to jail for no time than to go to jail for even 6 months. And so, again, we have the situation where the Nash equilibrium is for both robbers to admit to the crime, to defect on their agreement, even though there is this, what we would call, potential collusive outcome of 6 months. So you can see that it's almost the exact same scenario as the grade game. In fact, we would call the grade game a prisoner's dilemma. Again, sort of prisoner's dilemma here referring to a type of game as opposed to a particular game itself where we're only talking about robbers. Basically, the prisoner's dilemma, if we go back here, is a situation in which there actually is a collusive outcome that is preferred to the Nash equilibrium. However, because of the nature of game theory, we actually don't expect people to choose the collusive outcome. And it's because of a lack of trust. Generally speaking, the only reason you pick beta is if you think in a sense, that the other player is going to pick beta. But here, because there's this chance for both players to make A's when they think the other player is going to pick beta by choosing alpha, then that, on top of the fact that you open yourself up to that same risk by picking beta, this is why the alpha-alpha outcome would be considered the Nash equilibrium, and the beta-beta outcome would be considered a potential collusive outcome. So there's benefits to colluding, but ultimately the risks of being burned by colluding and the other player not colluding force individuals to pick alpha-alpha. And again, this is sort of the whole point of what John Nash was coming up with when he talked about non-cooperative games. And basically this idea that it actually isn't everybody doing what's best for themselves that creates the best outcome for the group, right? Because what's best for the group is for everyone to pick beta and everyone to get B pluses, right? So it's very similar to what happened when we played the public goods game in class. It was better for everyone to donate both of their tokens, but at the end of the day, you keep your tokens because of a sort of game theoretic, well, if I think everyone else is going to donate tokens, then I in fact do better by withholding of my tokens, right? We actually call this the free rider effect in public goods. We have a very similar thing here. In fact, sometimes people refer to public goods problem as a prisoner's dilemma, where, yeah, we would be better by cooperating with each other, but kind of natural human tendencies of self-preservation cause us to be rational. And as I've mentioned in class, sometimes rationality sucks. Sometimes rationality actually causes us to choose outcomes that we end up worse off than if we instead cooperated. Okay, so let's go on to another example. So in this particular game, we have another simultaneous game. Coke and Pepsi are choosing high prices or low prices. Again, what we want to do is we want to go through the strategy of the game, make our life very simple. So if we go through and we develop Coke's strategy, we ask ourselves, when Pepsi goes high, that puts us in one of these two quadrants. Again, the payoffs to Pepsi are the first numbers. The payoff to Coke are the second numbers. So if Pepsi chooses high, we're in one of these two quadrants. Coke chooses high, gets 80, chooses low, and gets 90. Now here, payoffs are profits. So the higher the number, the better. And so we can see that when Pepsi chooses high, Coke wants to choose low because 90 is higher than 80. Now, when Pepsi chooses low, Coke once again has an incentive to pick low because 70 is greater than 65. Now, on the other end of the spectrum, if Coke picks high, that means we're in one of these two quadrants. Pepsi wants to pick low because 100 is greater than 70. And if Coke picks low, then Pepsi wants to pick low again because 70 is greater than 50. And so the Nash equilibrium of the game, therefore, is going to be found when both players pick low. And again, the Nash equilibrium is defined as the outcome of a game in which neither player wishes to deviate from the strategy given the strategy of the opponent. So they ask themselves, if I think Coke is going to go low, does Pepsi want to do anything other than go low? And we've already established that the answer is no. And Coke asks themselves, if I think Pepsi is going to go low, do I wish to deviate from the strategy of going low? And the answer is no. All right, so here we have a Nash equilibrium. And we can check every other outcome of the game, and we can see that this is not true. So, for example, if we're in this quadrant, if Pepsi thinks that Coke is going to go high, they actually want to move to this quadrant, because going low is better for them, right? So this can't be a Nash equilibrium. Go here, we can see that when Pepsi goes low, does Coke want to choose high? And again, the answer is no. So this can't be a Nash equilibrium either. And the same thing here. If we check this, we can see that both Coke and Pepsi, or excuse me, that Pepsi would prefer to be in this quadrant over this quadrant. And so again, this cannot be a Nash equilibrium. This is the only outcome in which moving here would be bad for Pepsi, moving here would be bad for Coke, and then so therefore this would be the Nash equilibrium again. Okay, so again, this is what we would call two dominant strategies. Coke and Pepsi want to choose low regardless of what the other player picks. All right. Now here's a situation in which we do not have a dominant strategy. In fact, what we'll see here is that AT&T has what we call a mixed strategy. Let's first look at Verizon. We see that when AT&T picks high, that's in these two quadrants. Verizon picks high and gets 120, picks low and gets 110. Again, these are profits. Oh, excuse me. Again, these are profits. And so Verizon wants to pick high when AT&T picks high. Now, when AT&T picks low, we see that the answer is the same. Verizon would prefer to pick high. 90 is greater than 85. Again, the payoffs first go to Verizon. The payoffs second go to AT&T. So here are Verizon's payoffs, and here are AT&T's payoffs. Now, we have established, therefore, that Verizon has a dominant strategy, and that dominant strategy is to go high. Verizon will go high no matter what AT&T picks. And it's important here to point out that, again, in these games, we assume perfect information. That means that both AT&T and Verizon know each other's payoffs, and that's important. And we'll talk about why in just a second. Now, when we develop AT&T strategy, we ask ourselves, well, when Verizon picks high, that puts us in these two quadrants. AT&T picks high and gets 120, picks low and gets 110. 120 is higher, so when Verizon goes high, AT&T also wants to go high. Now, when Verizon goes low, we can see that, in fact, now AT&T wants to go low because they can go high and get 100 or go low and get 105. And so here we can see that AT&T, in fact, wants to go low when Verizon goes low. We call this a mixed strategy because when Verizon goes high, AT&T wants to go high. But when Verizon goes low, AT&T wants to go low. And again, here we're referring to AT&T and Verizon choosing prices, high versus low prices. So we would say that Verizon has a dominant strategy while AT&T has a mixed strategy. Now, the nice thing about Nash equilibrium is that we only need one dominant strategy. If we have one dominant strategy, then we have a nice, unique Nash equilibrium. Again, remember, both players have full information. So in a sense, AT&T knows that Verizon has a dominant strategy to go high, and therefore they will respond to that strategy by doing what's best for themselves. So again, AT&T wants to go high when Verizon goes high. AT&T knows that Verizon's going to go high. Therefore, the Nash equilibrium is for both players to go high. And again, we can check any other outcome of the game to see if there are not other Nash equilibrium, and we won't find any. Excuse me, do it again. So if we check here, we can see that, in fact, both players would rather be here, and then did it again. Sorry about that. And then if we looked here, we would see that AT&T would rather be, or excuse me, Verizon would rather be here than here, so on and so forth. And again, kind of given the strategies of the other opponents, we can see here that in this particular quadrant, neither player benefits from moving to another quadrant, and so this is our Nash equilibrium. Now, another unique thing here is that there is also no collusive agreement. There's no other outcome of the game in which both players do better than the Nash equilibrium. And you can see that, right? The Nash equilibrium, in fact, earns both players maximal profits. And so there's no potential collusive agreement. If we go back to this game, this was our Nash equilibrium, and we ask ourselves, is there a potential collusive agreement? And we can see that, in fact, the high price option may, in fact, be a potential collusive agreement. Pepsi is no worse off than they would be if they picked low, and Coke is better off. So we would call this a potential collusive agreement. This is the Nash equilibrium, but this is maybe a potential collusive agreement. Here we can see that there is no potential collusive. This is the Nash equilibrium, and there's no other quadrant in which both players do better, which is the requirement for a collusive outcome.